So the one before the break was the easy part. Now we're going to the slightly more modeling part. But actually, that's going to be this is going to be the more. Yeah, I'm losing my voice already. So sorry. So now we're going to see basically the part about diffusion tractography and advanced fiber modeling estimation, so that hopefully once you go back to your family and friends, you can impress them by creating these very fancy movies of, well, their own brain or somebody else's brain to show their white matter architecture at these unprecedented details, right? So this is a technique known as track density imaging, and we'll see later how actually you can get to these images given your, well, even very basic, very standard diffusion data sets that you can analyze using in vivo virtual dissection using tractography. So you see that basically what is passing through here, this is a movie created by Sajib Abdi in Oxford, and what we're showing you here is that at the resolution of 200 microns, so sub-millimeter resolution, you can start seeing the white matter fibers projecting coming out of a corpus callosum, for example, right? So you do super resolution starting from your acquisition, which was done at millimeter base resolution. We're going to talk about this a little bit later. Where we're going to start now is talking about advanced estimation of how you can estimate fiber orientation, so moving beyond the tensor that we described at the beginning. Then we're going to go to describe probabilistic tractography that we have also available. These are the two tools that we have available in FSL, so bedposticks and proptactics, doing the two respective parts. And then if we have time, we're just going to go through some tractography applications examples. Now to start, let's go back like a very small single slide recap of what we can do with a diffusion tensor model. Basically we can get pictures like this, right? So we can fit into each and every voxel our nice tensor. We can derive the principal diffusion direction using the diagonalization that I described before, and based on the assumption, once again, that water molecules diffusion correspond to axonal orientation, we can fit those kind of images, and we can use them to do tractography. But does this assumption, well, I'll give you a spoiler already, but does this assumption work everywhere in the brain? So if we look at these two, well, post-mortem dissected brain and consider, well, two prototypical voxels in two different spatial locations, we see that in these, can you see this? Yeah. So this voxel mainly shows only one fiber component, so the fibers coming from the corticospinal tract and projecting all the way to motor cortex, let's say. So you have one densely packed bundle of axon nicely and coherently following the inferior to superior direction, so along the z-axis. If we take another voxel, like here, you see that now we start having intersections of two different fiber populations, right? Fiber population projecting to the superior gyrus there, and the fibers of the so-called superior longitudinal fasciculus following, well, the Y orientation, right? So to the anterior, to the posterior part of the brain. So what we have actually is that given our resolution, given our millimeter resolution, we have to find a way to deal with these complex subvoxel fiber configurations, right? So to understand, like, once again, to go back to the modeling perspective, which is what we ultimately want to do, is let's take some typical example. Let's try and model some typical examples of fiber configurations that we can find anywhere in a typical brain. So let's start from the easy bit. Let's start from a voxel in which you have only one clear fiber population following the orientation along the black stick, right? So this is what we're going to fit into that voxel. If we want to look at the three-dimensional signal profile that we have acquired from our scanner, what we are going to expect, what the simulation gives back at us, is that donut-like shape. If you remember what I said at the beginning, what that donut-like shape tells us, what it's showing us, is that you have the highest amount of signal loss, of signal decay, along the black stick. So you're losing most of the signal along the orientation of the black stick itself, right? Which in a scenario one fiber population, that's exactly what you expect, right? Water molecules diffuse, you lose signal. And that is the only orientation that you have. Therefore, if we fit our diffusion tensor in that voxel and we use our, well, estimated diffusion tensor estimate to predict the signal. So I go back to my original equation. I have estimated D, and now I can derive S, the intensity of a signal, and I plot it, and I reconstruct the three-dimensional shape of it. They nicely correspond, right? So reality, the measured signal, nicely correspond to what I'm able to predict, meaning that my model fit is pretty good, right? Tensor is giving me a good result. If I look at the DTI ellipsoid, so after diagonalization, we have clear anisotropy, cigar shape, right? One principal diffusion direction. If we now take a cross-section, so a plane along the XY orientation, and we look at the prediction, so this guy over here at the red surface, and we start putting the intensity, the measured intensity that are discrete, of course, because you only sample a certain number of volume on top of the surface, they nicely fall on top of that, of this specific cross-section, right? So once again, nice confirmation that our model is giving good results. Let's now complicate the scenario a little bit more, right? Let's now consider a different voxel in which you have two fiber crossings at, let's say, exactly 90 degrees, so on a plane, right? Already here, if you look at what you're actually measuring, so at the measured signal profile there, you see that if before you were immediately able to, well, predict that the axons were running along a certain orientation, the scenario changes here, right? Because actually here you have the highest amount of signal decay, not along any of the two orientation, but you actually have it along the diagonal, right? As if it's telling you, I have only one fiber population that cuts through these two equally prominent fiber populations, right? So you fit the tensor once again. Tensor gives you also a completely different shape from the measure that you have. The DTI ellipsoid collapses to, well, the pancake shape that I was describing you before. So tensor desperately, well, can only estimate one direction, but it tries to tell you that there are actually two, but it can tell you exactly which one are those, so it only gives you the plane. And once again, if we take a cross-section here, we see that the prediction along this cross-section is circular, and the measurements don't fall anymore on the predicted signal shape that you have. Now you've got the rationale of these. We complicate the things even more. We have three fiber crossing at 90 degrees into a different voxel. Measure signal shape completely doesn't give you any information anymore about the signal decay, any meaningful signal decay from which you can immediately infer the axonal orientation. You fit the tensor. The estimate, the predicted signal shape that you get out of a tensor is a sphere, so tensor gets completely confused here. DTI ellipsoid is a sphere, which, if you remember, is the shape that we typically get into CSF, while here we are simulating white matter voxels. And once again, taking the cross-section and overlaying the measurements, we do get a bad fit. So how can we, try to put those three different shapes into the context of a brain? We take here another cross-section, well, one of the same cross-section that I showed you before. We look at the three different areas, so taking the simple one, the body of the corpus callosum, very good fit, very good prediction of our tensor shape, so cigar shape right here, very clear anisotropic behavior. We go here at the bottom, at the level of the pons, where you have the corticospinal tract fibers running from the bottom to the top of the brain, but you also have what they're called the transpontine fibers running along the left to right orientation, so two fiber crossing at 90 degrees, on which the tensor shape collapses into a pancake. And then in the central semiovale, where you once again have the callosal fiber coming from here, corticospinal fiber running from here, and the superior longitudinal fasciculus coming out of the screen, so three fiber components crossing at 90 degrees, again, tensor collapses into a sphere, right? So what you actually can say from these two different scenarios is that the principal diffusion direction that you estimate is basically meaningless, right? Can't use it to do, well, basically tractography. And even the FA map here will show variations in intensity which shouldn't be taken for, well, effectively deviation from normality from a healthy brain. Moreover, what you also have when you do this sort of modeling approaches is that and this is a crucial thing that's going to come back over and over in this part of the talk, is that once you estimate your principal diffusion direction, you have a certain degree of uncertainty about it, right? So that is kind of reflected by the fraction isotropy measure that we saw so far. And this uncertainty actually comes from two sources. It comes from the noise, natural noise that you get in any acquisition, right? Given by the scanner signal profile, the day that you scan your subject, eddy currents, you name it. But you also have the modeling errors, right? Because, as it usually said, all models are wrongs, but some of them are useful. That is definitely the case for the diffusion tensor model, but it also introduces some noise just because of its imperfection of the model itself, right? How can we translate visually the uncertainty in our estimate? So if we look at these maps, these are maps of the so-called uncertainty cone. And if we look at this area, at these two different areas in the brain, once again in the axial slice, we see that the uncertainty cone is very small, it's almost imperceptible in the corpus callosum once again. So again, densely, tightly packed white matter axons. But at the moment in which we reach an intersection of two fiber population and we use the diffusion tensor model, you see that the uncertainty cone kind of explodes. Well, it becomes significantly bigger. It definitely explodes in the CSF areas, right? Where you definitely are not sure that the principal diffusion direction estimated is actually meaningful. And if we zoom a little bit more here, you see that this cone basically becomes significantly bigger once these two fiber population cross with each other. And luckily, we're not just limited to use the diffusion tensor model, which is still very useful, as we're going to see later in the talk, but especially when we're interested in doing in vivo virtual dissection. So if we're interested in tractography, we can use more advanced models. And one of these is the so-called ball and stick model, which is what the bedpost-sticks toolbox uses to estimate fiber orientation in FSL. And what this basically is from, the mere mathematical modeling point of view, is that it's an extension of the original exponential equation that we had at the very beginning. So, if you remember it, that's basically what we had at the very beginning. So we still try to model the measure signal for the gradient orientation. We have the exponential of the b value and the orientation x. But now you see that we have two exponential. So we're trying of distinguishing two different compartments of water molecules. We're trying to describe an isotropic compartment, so the ball, so the water molecule's fraction that is free to move at that specific spatial location. And we try to combine it with the exponential, with the compartment. This is why we call it a multi-compartment model. We try to model the purely anisotropic, so the stick volume fraction, right? And that's why the first exponential doesn't have any dependence on the unit vector that represents your diffusion encoding orientation, but it only has a dependence on the b value and on the d, on the diffusion coefficient, while we introduce the dependence, the orientation dependence, in the anisotropic compartment, right? And we do weight these things by f, which is the so-called anisotropic volume fraction. And basically it measures how much of a signal is explained by the anisotropic compartment in comparison to the isotropic compartment, right? So is the signal in that voxel mostly dominated by free water, or is it mostly dominated by anisotropic behavior of water molecules? And effectively what we try to estimate when we do this model is once again the anisotropic volume fraction f, the diffusivity, so not the tensor anymore, but just a scalar in this case, and the fiber orientation, the red V here. Right? So these are the parameters that we want to get out. So not just the tensor anymore, but these are the parameters that we tried to get out from this model. And the nice thing, the ball and stick model, is that you can kind of immediately see that it's very easy to expand, because now we're not limited to have only one stick, so one clearly anisotropic compartment, but we can have multiple of them. So rather than having only one volume fraction, we have a summation of n volume fraction, right? N being a number from, well, typically 1 to a maximum of 3, being 1 to 3 fiber populations that you're capable of fitting into that voxel. So once again, get the measure signal, b-value, and what you're trying to estimate are effectively the red letters, the red quantities there. And if we go back to our simulations and we compare how well we're doing with the diffusion tensor model compared to the effectively ball and multiple sticks model, we see that in the more complex scenarios of a 2-fiber orientation and 3-fiber orientation crossing at 90 degrees, you get, well, a very bad fit between the predicted signal and the measure signal if you were to use your DTI model. But if you now use this equation and you try to predict S, so the signal that you measured, you actually get a very good fit between the prediction, so the red surface, and the measured blue dots that you get out of your scanner. So it is already quite a gain in terms of signal representation, goodness of fit, in respect to the diffusion tensor model. Now here it is, the uncertainty concept comes back, and I was going to see in a second why. This is just if you were to try to estimate some fMRI quantities, and you were interested, sorry, should I check these transitions? And you were interested in estimating the uncertainty about the beta values typically that you estimate in fMRI. That's very easy to do. There is an analytic formula to do that when you do simple linear regression, so when you apply the so-called general linear model, which is what the typical basic analysis of fMRI data allows you to do. You don't have that kind of, well, luxury when you want to apply this kind of modeling approach that I just described for diffusion MRI data. You don't have just the GLN, but you need to use a slightly more advanced framework to estimate the variables that we're interested in. And in the case of bedpost sticks, what we do is that we use a so-called Bayesian probabilistic framework to get the interesting quantities out of it, which basically means that we have our data sets, we have our generative model. What the generative model effectively is the equation that I just showed you before. So you have a way of modeling your signal, and you can also account for noise. And by performing Bayesian inversion, so a probabilistic inversion, let's forget about the details here for now, but keep in mind that it is a probabilistic framework, so it's not a simple computing the fraction or an analytic formula to estimate this. What you can get out of this is a whole distribution about the parameters of interest that you have in your model. So it's not just that in every voxel you now have one number for D, but you're actually going to have a distribution of likely values that D can have in a specific voxel, right? If you were to use this, once again we're here, if you were to use this framework. So we can have the so-called posterior distribution of our parameters of interest. And what having the distribution basically gives you is that it's not just a single value, it's not just the average value of the expected value that you're going to get for that parameter, but you also, given the standard deviation of this normal distribution, you can also have the estimate of how certain you are about that parameter value, right? For all of the parameters that we have there. So what effectively means is that we don't need to rescan the single subject 100 times to quantify the uncertainty, but we can do that for a single data set. And if we now look at two different voxels, one in deep white matter, like in the body of the corpus callosum, and one in gray matter or CSF, we see that our sticks, our anisotropic compartments, will show a very low degree of uncertainty. So you are very sure that water molecules will tend to diffuse around that orientation, while this uncertainty will basically explode in a gray matter CSF voxel, right? Just because water is basically free to move everywhere around, everywhere it pleases around in that specific spatial location. And once again, if you were to break this down into the ball and stick model that I presented before, so the multi-compartment model, you will have effectively a distribution of isotropic compartments of the balls and a distribution of sticks of anisotropic compartments. right? And if you were just to collapse them on top of each other, what you basically have is the representation of the uncertainty of a diffusion direction, but of the diffusion, principal diffusion direction that you estimated in that voxel. Of course, now the question becomes, how do you select? Because what the user does when anybody uses bedpost-X is that it specifies how many fibers you basically try to estimate in every voxel, and you typically set that number to 3. But now, is there a way to actually let the algorithm decide whether in one voxel you should have 1, 2, or 3 fiber compartments? And we can embed that into the Bayesian framework that I just presented. It's basically, sorry, comes down to using a different prior, which is called the automatic relevance determination prior, but basically automatically determines the most likely number of fibers that you have in each voxel. And the basic way that it works is that once again it does this comparison between actual sample data and predicted data that you have. So we are in a certain voxel, our diffusion profile looks like that, so all the signal goes up and down depending on the diffusion anisotropy behavior. And if we model this signal with 1 or 2 stick, so we're able to predict the signal following the blue line, we don't have any significant gain between the two different modeling approaches, right? While if we're here in more complex voxels in which, for example, 2 fiber crosses, we see that modeling just using 1 stick doesn't do enough of a good job as modeling the same voxel using 2 sticks, right? So the prior basically automatically decides that yes, in this voxel you should retain the 2 fiber information, while here you should basically bring the anisotropic volume fraction of a second fiber to effectively 0, right? And this is automatically done by the Bayesian framework that you've set up in bedpost-X. What do you get out of the analysis? You basically get the estimated orientation of the fiber population for the 3 different sticks, so the independent ones, and you also get the anisotropic volume fractions that have been rescaled by this automatic relevance determination prior, right? So that if you were now to threshold the volume fraction for, let's say, 5% of explained signal, you see that only very few free fiber crossing population will survive that threshold. So effectively what you do when you do bedpost-X is that you are going to fit 3 fibers, but the anisotropic volume fraction is going to be brought all the way back to 0, so that you can effectively threshold it and only retain the useful information. And if you were to zoom on the usual suspect area, so once again with centrum semiovale, you see that in this case we have the callosal fibers coming out of the body of the corpus callosum and fanning to reach the contralateral cortex, but we also have the corticospinal fibers in blue, and well, roughly you can see the 3rd fiber component in green of a superior longitudinal fasciculus. Yes?
Even if you set the ARD to 4, it wouldn't matter. Most of the time it'll just consider it relevant. It takes a
You mean in the toolbox when you use the well, that's a different thing. You can set it between 0 and 1, and it actually tells you how dominant the ARD should be.
So if you're modeling for 3 fibers, I think that's the new point. So suppose you change that to 4. It's going to 0 out of all that anyway, most of the time.
Probably yes, but just because typically you don't have a kind of angular information. You don't have enough angular information to model like more than 3 fiber components. At least I've never seen it, but yeah. But in that case, again, the RD will kill the 4 fiber component by definition. Yeah. But it's not that it's doing it automatically because you set out 4, but just because you don't have enough information in your signal to represent the 4 fiber population. Yes.
In the bedpost, the default parameter is 3, like the
For, yeah.
population. Do you think that it's enough for you to just see the complex of the white matter crossing fiber?
Let's again, that's typically the maximum you can do anyway.
It's enough.
Whether it's so rather rather than including more fiber components, what you usually can do is expand your model and start to introduce like concepts like fiber dispersion and these kind of things to try and model like fiber fannings and these kind of things. So estimating more than 3 unique fiber compartments is tricky. Yes?
From a model perspective, can you please explain what is the difference between the Probabilistic model and other models such as constraint, spherical interpolation, spherical harmonics?
Sure. We can discuss about this a bit more in detail later if you want, but to give you like an idea of the difference, what effectively the ball and stick is a spherical deconvolution approach, right? Because you do have a kernel which is via an isotropic stick, which is the stick model effectively. The main difference between this spherical deconvolution that is done in bedpost sticks and the constrained spherical deconvolution approach based on a spherical harmonics basis typically is that the bedpost sticks approach is the so-called parametric approach, and the constrained spherical deconvolution is the non-parametric approach, right? So that is basically the main difference, is how you get down to the estimate of the parameters given these two different models. Given that the parametric approach, bedpost clearly defines some, well, let's say, even though they're not microstructurally relevant, but some, let's say, microstructurally relevant parameters, diffusivity, fiber orientation, and so on and so forth, while for constrained spherical deconvolution, you have a spherical harmonics, which forms an orthonormal basis on the surface of a sphere, right? So effectively what you're trying to do is, given a basis, you just try to fit the coefficients of that basis. You just try to estimate the coefficients of that basis, right? Yeah, but that's a very, very good question, actually. Anything else? Yes?
And the two approaches will be equivalent if there were only 3 fibers.
And hopefully they should be equivalent. The only thing is that typically with constrained spherical deconvolution, you're going to estimate a surface, while with bedpost, you will have 3 clearly defined fiber populations.
But you also have the variance, the uncertainty.
You're, exactly, plus with bedpost,
Also like a surface.
exactly, plus with bedpost, you're going to have the uncertainty. Ultimately, it is going to be a surface, but it's not parameterized as a surface, right? Yeah. And if you do like the most basic comparison to compare the diffusion tensor approach and the ball and stick approach, you see of course the increased wealth of information that the ball and stick model gives you. So saying that basically the principal diffusion direction that you estimate out of a diffusion tensor should roughly correspond to the orientation of the first stick, so in red here in the ball and stick model, but then of course you lose the information, or actually you get completely, well, almost meaningless, let's say, information out of a DTI model in regions where fiber tend to cross, while you actually reconstruct the crossing correctly using the more advanced model. And how can you be sure that actually, well, all this modeling is meaningful? Well, one way to ensure yourself that what you're actually, the fiber populations that you're estimating are meaningful is that they should show a certain degree of spatial coherence, right? So once again, if you start from a location and you try to connect the dots, those fiber populations should nicely be aligned along the path of the fiber itself, right? So all the reds are roughly aligned, they're continuous in space, and the blue ones as well. Right, so this was about advanced fiber modeling. So if you don't have any question, now we can move to the propter kicks, so to the probabilistic tractography. How do we perform probabilistic tractography, at least in FSI, using the propter kicks toolbox? And first of all, well, price of why we should be interested, why we should be doing structural connectivity studies, so estimate the structural connectivity profile of the brain. And that can be, once again, because we're interested in certain diseases. So for example, in this nice representation by Catani done in the paper in 2005 shows you that depending on which white matter connection is interrupted, these can give rise to different language deficits, in this case, like apraxia or aphasia and so on and so forth. So given the disconnection between two brain areas, you can elicit different pathologies. So that's why you might actually want to probe the white matter connectivity in vivo. You can do longitudinal studies or cross-sectional studies at the single white matter fascicle level, and combine the structural connectivity information with the microstructure information. So looking at the track-specific developmental microstructural profile and see how it changes, how actually it becomes different from track to track inside the brain and how it changes across the human lifespan. And of course, another thing is that you might be interested in comparative studies between human and macaque, for example, and try to define homologous region between the two species, or just like in this example, define two different areas, like in this case F3 and F5 in the macaque cortex. Try to define two different areas based on their structural connectivity fingerprint, right? So two two pieces of cortex within the same animal will show different projections, different upframe projections. And if you want, you can basically now cluster these two areas based on their structural connectivity profile, right? So you can do area definition using your structural connectivity contrast. And furthermore, why tractography is very powerful? It's also because you have several approaches to do invasive structural connectivity mapping by injecting different kind of radioactive compounds, for example, or do lesion studies, while actually tractography is the only, so far, in vivo tools that allows you to study these connections in vivo in a non-invasive way using just your MRI scanner. And what it comes down, what actually tractography is that it corresponds to the virtual dissection approach that has been used by anatomists to describe this white matter connectivity profile, but doing this, again, in an in vivo, non-invasive fashion using your diffusion MRI images. So that now you can segment white matter tracts using the diffusion MRI data that you've sampled during your experiment to perform what is known to be, again, the so-called in vivo virtual dissection. But of course, also tractography, like the diffusion tensor and like all the other models, is not perfect. So it's very nice because, like I just said, it's non-invasive. You can do it in vivo. You can map actually the whole brain, so you're not just constrained to a single postmortem slice or a single postmortem hemisphere and so on and so forth. But again, you can map the whole brain. You can address a series of questions like the ones that I presented to you at the beginning. But of course, it suffers from being low resolution, right? So we're bounded to the millimeter resolution that we acquire for, sitting behind the MRI scanner. It's indirect, once again. So always remember, it's water molecules here. It's not actually white matter axons that we're probing, that we get the signal from. It is error-prone. It is error-prone because of the presence of noise that we described before. And it's also very difficult, given all of these factors, to interpret it in a quantitative fashion. Right? I'm going to discuss about that a little bit later, but always remember that it's difficult to say area B is more strongly connected to area B rather than to area C, or compare across the different subjects. Now, how does tractography basically do? Like I hinted at before, using, for example, the simple DTI model is you're roughly connecting the dots. So you start from a seed region and you construct the path tangent to the principal diffusion direction. For the more mathematically inclined, this comes down to numerically solving this differential equation. So given a certain starting conditions, a certain starting position, such as the seed region that we defined there, we basically try to equate the derivative, the first derivative, so the tangent to the curve at a certain position with a principal eigenvector that we estimate out of a probabilistic model, or in this case, out of a DTI model. And of course, the question becomes now, because this is what we do, these are all the algorithms that we do, that we program, that we set up while sitting behind our computers, the question becomes when to stop, right? So you initiate a streamline, but where should it track to, right? Should it go out of the brain? Should it transfer CSF regions, and so on and so forth? And a way to define, from an algorithmic perspective, a way to define stopping criteria can be imposing a certain curvature change threshold. So you don't want your streamline to suddenly bend at more than 90 degrees, for example. you can impose an anisotropy threshold. So using the combination with, for example, Probabilistic and diffusion tensor model, you can say stop tracking when FA goes below 0.1, let's say, because low anisotropy means that it's probably an area of gray matter or even worse, CSF. Or you can impose some anatomical criteria, right? So let's say that you have defined a gray matter mask, and you basically just tell your algorithm stop tracking once you enter this mask, right? So only track when you're within white matter. And even if you do this very simple approach, you can get some very nice results. So once again, this is the Atlas example that I showed you at the very beginning. And using DTI, so-called deterministic tractography, so we haven't gone into the probabilistic part just of yet, but you can segment out the arcuate fasciculus, cingulate bundle, fornix, corticospinal tract, and so on and so forth, right? So even with this very simple tool, you can already do some pretty spectacular things. So just as a quick summary for this initial part, if you want to do DTI Streamline Deterministic Tractography, what you do is that you use the principal diffusion direction, so the main eigenvector out of your diffusion tensor estimate. You will propagate effectively the streamline until the criteria, the anatomical criteria, or the algorithmic criteria that you set up, and given these, basic, relatively simple approach, you can already reconstruct some major white matter fiber bundles. But let's now go back to this idea of uncertainty and reproducibility, right? So let's go back to the uncertainty cone that we had before, and let's say that I take one subject, and I put him or her in the scanner for 100 times, right? So I do 100 acquisition of exactly the same subject. How sure can I be, how certain can I be about my structural connectivity estimate? I can basically, given exactly the same seed point across all of these acquisitions of the same subject, I can launch my tractography algorithm, and I can derive such a map, such a reproducibility map, that basically tells me simply how many times have I gone through the same voxel, given all the acquisitions that I perform. And you see that if I just were to look about the nice 3D pictorial representation that I have here out of a single analysis of a single data set, I don't have a way to say which path is most likely than the other one, given that seed region. Well, actually, if I repeat the experiment hundreds of times, I see that I'm really sure that given the seed region, I will probably terminate somewhere here, but I'm very unlikely to project to the front or to the posterior part of the brain, right? So here we go back to this idea of uncertainty, and like in this case of reproducibility and producing a low and high reproducibility map. And how can we translate? Of course, we don't want to spend that much amount of money. We don't want to put the same subject in the scanner for hundreds of times. But how can we get similar path probability maps in this case? And basically one way to do this, and one way that we can do it using the bedpost-X Propagating combination in FSL, is that, again, of course, we normally have only one data set from each and every scanner that we scanned. And what we can do is that we can use not a deterministic approach, like the one I presented when I was talking about the diffusion tensor, but we can use a probabilistic approach. So we recover the uncertainty in the fiber orientation using the framework that I described before, and I use this estimate of uncertainty to build the path probability map that I just introduced now. And what this basically means is I don't want to do just effectively a single streamlining, but if you remember, now in every voxel, I don't just have a single estimate of a principal diffusion direction, but I have a distribution of sticks. I have a distribution of orientations for all the fiber populations that I estimate. So now, given a starting point, I can start throwing thousands of streamlines, and each and every streamline will see a different estimate of a different orientation of that voxel, that in this voxel will be very constrained, but will explode in this voxel, for example. So I start throwing all the streamlines that I have, and this is roughly the result that I get. I don't have just one orientation, so a single streamline that will run upward, but I also have the fibers that will start fanning and reaching different areas of the cortex, thanks to the uncertainty estimate that I get out of bedpost 6. More precisely, well, in a cartoon example, how actually probabilistic tractography works. This is a scenario, a brain scenario, that we can have out of a bedpost 6 analysis. So we have a series of voxels, a grid of 3x4 voxels, and now in each and every of these voxels, I have a distribution of sticks, distribution of anisotropic compartments, right? So how probabilistic tractography works, given a question of is voxel B connected to voxel A, is that once again, it starts throwing thousands of streamlines, right? So we start from voxel A, we take one estimate of the principal diffusion direction, one stick out of the ensemble, out of the distribution of stick that we have, and we start tracking, right? We reach the voxel boundary here, and we start seeing this voxel, right? We take one stick out of the distribution, and we keep tracking, right? Until we see another boundary, we see another voxel, and we do the same thing. We take one stick out of the distribution, and we keep tracking, right? So on and so forth, like this, for all of the boundaries. So this is our first streamline. We start again from voxel A, and we throw another one, but now at every step, every time that we encounter, every time that we enter a different voxel, we take another estimate, another stick estimate out of the distribution that we have, right? And if the first streamline didn't hit voxel B, the second one already does. But we actually want to do this in a more, well, we actually want to extract some quantitative connectivity information, so we do this again, hundreds and thousands of times, right? So that in the end, what we can get is we can compute the probability of A being connected to B as simply the ratio of the n streamlines that make it to B divided by the total number of streamlines that we initiated from A, right? So we don't have, like in the tensor deterministic case, a 0-1 information, connected versus non-connected, but we do have a weight, we do have a probabilistic likelihood of connection given the approach that I just described. Now let's see again, why is this uncertainty very important, and how can this uncertainty actually help us in modifying the connectivity weights? Let's now take the same grid, but imagine that between voxel A and voxel B, we see, well, let's say the ventricles, right? Where there's an explosion of uncertainty, water molecules are free to move in any possible direction. How does this affect our probabilistic result? What is going to happen is that, yes, maybe the first streamline will make it to B, but now given that we have a much higher uncertainty, a much wider distribution from which we can sample the orientations, this will tend to go all of the way, right? So if you think about before, now the connectivity between B and A is reduced just because you had this higher uncertainty area in between the two regions that you're interested in. So that's why the uncertainty estimate, that's how the uncertainty estimate can help you in determining the connectivity scores between the two voxels. And of course, this probabilistic approach can be expanded to the presence of multiple fibers in every voxel. And on the left-hand side is the case where you have, well, only one fiber population in every voxel. On the right-hand side, you have where you have up to 2 fiber populations in every voxel. And the only thing that you do in this case is that once you enter a new voxel, you don't sample just a fiber orientation from one population, but you sample out, well, 2 samples from the 2 distribution, and you select the one which is most collinear to the direction you entered in when you were coming from this voxel, and you just continue propagating the streamlines. Why is this useful? Why should we account actually for multiple fiber orientation in every voxel? Well, once again, because crossing occurs quite a lot at the resolution at which we sample our data. And let's take here an example in which you have fibers from the internal capsule projecting to the primary motor cortex, so the corticospinal tract fibers, and these are crossed at the centrum semivalley here by the superior longitudinal fasciculus in a 90-degree fashion. You see that for 9 subjects on the left-hand side, if you were not to account for the fiber crossing, you won't be able to reconstruct the lateral projections of the corticospinal tract. That you know that anatomically should be there, but you cannot see them if you have a crossing scenario and you don't account for it in your modeling. An even more severe case is fibers coming from the little geniculate nucleus and projecting to the primary auditory cortex, and which cross, again, let's say in a schematic 90-degree fashion with the optic radiation. In this case, if you're interested to virtually dissect the fibers reaching the primary auditory cortex, if you don't account for crossings in the same 9 subjects, basically you won't be able to see them, to extract them at all. So basically this is the way on how we can get our path probability maps. It tells us how reproducible, how sure we are about a structural connectivity between the seed region and the rest of the brain. They're often called in publication connection probability, connection strength, index, so on and so forth, but it doesn't tell you anything about the strength of a connectivity between 2 regions. It just tells you something about how reproducible your results in. So you should be very careful when comparing them in a population, in a subject population. And this is where the question comes in, right? But yes. 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 No, exactly. So this is the scenario that you're basically describing, right? So we're starting from here, we start propagating, and let's say we see this voxel, right? Yeah. So we do something like this. We take out, we have a distribution, we have a 2-fiber distribution. We take 1 stick from this distribution and 1 stick from the other distribution, right? So what you see is effectively this. And you propagate along the most collinear one, right? Because, again, it is true, maybe anatomically, these fibers can also take the 90-degree turn, but it is very unlikely, right? So what you tend to do is that you tend to follow the most collinear one, given a certain angular threshold. So to go back to the, well, one of the most interesting questions from a neuroanatomical point of view, what actually is, even from the anatomy point of view, what is a quantitative measure of connectivity? Is it the number of axons that connect 2 areas? Is it actually the relative proportion of axons that from the seed reach the target, so the probabilistic numbers that we get out of it? Or is it actually the integrity of this white matter connection? So degree of myelination along the path, conductivity, so on and so forth, you name it, packing density like here. The only thing that we have is actually the probability of a dominant pathway that we sample out of our diffusion field. It's the only information that we got. Yes, we get a probability, but it's not a given that will reflect any of the previously mentioned neuroanatomical measure of connectivity strength. What they actually depend on is that your probability, well, your estimated structural probability weights can depend on several factors that you're actually not interested in. Typically, the probabilities decay with the streamline length. So let's say that you're interested to track the fibers that run from the posterior to the anterior part of your brain. They need to travel quite a long distance. Given the noise in your measurement, they will go through areas which have different degrees of uncertainty, which can be high, low, and so on and so forth. So actually, you're going to get very low probability weights between the posterior and anterior part of your brain, but these just reflect the noise that you have in your data set. They don't reflect any neuroanatomical grounded concept of structural connectivity between the 2 areas. They can also reflect geometric complexity, right? Like in the example that I gave you before. We start seeding, we're very close to an area where uncertainty explodes, and just because of that, our probability weights will decay, will be lower once again. But it also depends on the resolution of the spatial grid, right? I said at the beginning that we always acquire, well, our data set at different millimeter resolutions, right? And given the sampling that you perform of your space, you're going to get different answers when it comes to probability weights. To give you, well, a more grounded way to see this dependence on the spatial resolution, try to imagine the probability maps that I saw before, so the volume, try to collapse that into an histogram, into the distribution of the probability weights. If you do that, if you just use a different histogram to represent exactly the same data, so you perform your streamlining at 2 mm resolution, but now you actually do the counting on a different grid. You resample your data set from, let's say, 2 mm isotropic to 200 millimeters cubes, right? And you once again count the number of streamlines that passes through, well, that nicer grid. And this is basically the only thing that, well, the main thing that track density imaging does. It regrids your original results. But even if you do this rather simple approach, it's going to act like a sort of super resolution algorithm. And now, given exactly the same structural connectivity mapping that you perform at the beginning, you start seeing the intersections, the crossing of the white matter fibers at a much higher resolution, with the corticospinal tract nicely crossing the callosal fibers, which are actually fanning to the contralateral hemisphere, right? So you can get these kind of results not by actually sampling 200 micron voxels, which not even the best scanner in the world can do at the moment, well, unless you're doing post-mortem rodent work, of course. But you can actually get that by using the structural connectivity information that tractography gives you. And just by simply collapsing these path probability maps to a one-dimensional histogram case, you basically observe where that results come from, right? So what we're doing here is giving the basically same histogram with many streamlines being sampled or few streamlines being sampled. We see that if we use a coarser grid, it becomes very difficult to distinguish the two different distributions of the histogram. But it actually becomes much more clear once we make the bins much smaller, which is exactly the same as regridding the original spatial grid that we have. But of course, you're also going to get, and this is the dependence of a structural connectivity weight on something that you're not interested in, the numbers, our probability weights will change depending on the grid size, on the binning size that we use. And another thing, of course, that is typically done when you do tractography studies is that you do add some prior knowledge before tracking. So this is typically translated in terms of different masks that you can use, waypoint exclusion and termination masks. And basically this translates with how these are used into any experiment in which you're interested in extracting a certain white matter bundle. So that let's say that you're interested in extracting the corticospinal tract out of your patient or healthy population, right? You start seeding in the primary motor cortex. So place the seed in M1, specifically in the end area in this example. And if you were not to add any prior information, you see that, yes, the most likely path follows the corticospinal tract, but you also get some spurious fibers going through the corpus callosum and reaching the contralateral hemisphere, which you know shouldn't be there. So what you can do is that you can set an exclusion mask saying block all the fibers that cross the mid-sagittal plane, that go through the corpus callosum in this case. And this already gives you a much cleaner result. Another thing that you know from anatomy is that the corticospinal tract should go through a very narrow area, which is the so-known internal capsule. So you actually put a waypoint area, a waypoint region of interest, ROI, and you actually extract a much better picture, much better reliable picture of your corticospinal tract out of your single subject, like in this case. Another example, you're now interested in the corpus callosum, so the fibers that actually breach the contralateral hemisphere, but actually there you go. You get also this spurious connection along the corticospinal tract. And once again, what you can use here is the so-called waypoint mask. So you're actually telling the algorithm, only keep the streamlines. When you return the path probability maps, only retain the streamlines that go through the body of the corpus callosum, so through the green region, right? And there is the U-shaped corpus callosum. So, as a summary of this part, what probabilistic tractography needs is the uncertainty estimate that you get out of the Bayesian framework that we set up for bedpost sticks. What you effectively do, and this is why it can take a long time unless you have a GPU or graphic processing unit on your computer or server, is that you propagate thousands, hundreds of thousands of streamlines repetitively from a certain seed region, and what you get in the end is a connection probability between region A and region B. But once again, interpretation is tricky, right? This is a probability that you get out of your virtual streamlines, but should be handled with care and based on a certain hypothesis. So to conclude this talk, only 10 minutes later, briefly some basic tractography applications, right? So the basic one being this idea of connectional contrast that you can get if you were to do a tractography reconstruction. So let's take a T1 weighted scan, a T1 weighted axial slice, like in this case from a subject. Beautiful contrast, very high resolution. But if you were to segment, if you were to extract the bilateral thalami, so the left and right thalamus, it becomes quite tricky, right? You have a very low signal to noise ratio, specifically in that area. What tractography is actually capable of giving you is this idea of connectional contrast. If you start seeding from the different voxels within the thalamus, you will see that depending on where you are, you will start projecting to different areas of the cortex, right? So if you start seeding from the ventrolateral nucleus of the thalamus, you will most likely reach the primary motor cortex, while if you start seeding from the mediodorsal nucleus of the thalamus, you are most likely going to reach the prefrontal cortex, right? Imagine that you apply these concepts throughout, well, the whole subcortical structure. You can get in vivo a map of the different nuclei of the thalamus, which are basically invisible when you perform a T1 weighted acquisition. So this is the idea, this is what we call the connectional contrast. And this approach has been used in a paper by Tim Behrens, where he basically used tractography to parcellate the thalamus in its different nuclei and validate that against well-known neuroanatomical knowledge. And of course, this has been taken and expanded to parcellate different areas, well, different cortical areas and different subcortical structures in other studies quite successfully, and while comparing to prior anatomical knowledge or, well, between different species and try to look for homologous areas and regions. We can look, as I said before, and like we did in the baby connectome, you can look at structural brain development. So now you can combine the microstructure information that you get out of your diffusion weighted data, so information about fractional isotropy, mean diffusivity, or more advanced model, the intraneurite water fraction, so which sort of measures what should be a proxy for axonal packing density, or the concept of fiber dispersion. And you can map these microstructural features to the different tracts that you're able to dissect in vivos from, in this case, the baby cohort, right? So you can compute an average within a certain mask, within a certain tract-specific mask, and now you can plot it on a temporal axis. So you have the different stages, well, different weeks of development, 38 weeks, 40 weeks, 44 weeks, which is the age at which the baby has been scanned. And if you were to put this tract-specific microstructural average and plot them against two microstructure informations, without any prior information about which tract category every single tract belongs to, so whether it's a projection tract, limbic tract, callosal tract, and so on and so forth, you see that in terms of development, they do form some nice clusters in terms of their microstructural features, pointing towards the fact that development happens at different time points. So different brain networks, different brain systems develop at different time points during early development, right? Being the main ones, of course, developing earlier, so motor, sensory networks developing at an earlier stage, and association areas being connected at a later stage of development, connected and myelinated at different stages of development. And what the arrow shows is the change, the rapid change in just a week time of these microstructural features in the baby cohort. So you see that you have quite massive and rapid change on a week-by-week basis. Another big question is, of course, okay, can we now trust these like beautiful, colorful results that we get out of tractography? The answer is always, of course, with care, given that our models are limited and tractography is limited per se. And we can imagine different scenarios in which our, well, diffusion direction estimate will fail. So let's say that, well, the most basic, the happy scenario in AVOX, in which we have a certain bundle of fibers running very nicely parallel and densely packed to each other, tensor and ball and stick model perform very well. But then you complicate the thing and you start having fibers fanning, and neither the tensor nor the principal diffusion direction that you get out of ball and stick will tell you anything. You get crossing, and the tensor doesn't tell you anything about it, but the ball and stick actually tells you that there are two fiber populations here. But if instead of crossing, you have two fibers, let's say, kissing, so still forming an X shape, but actually being completely independent between each other, even the ball and stick model will still give you the cross, but it won't tell you actually which path, which endpoint you should connect with each other. Or even fiber bending, it's going to be the same, because it will always see these two endpoints, right? So it will represent it as a cross rather than a sharp angle in that box, which will lead to some, of course, imprecision. So if we know that, if we now have a free region scenario and we know that this is actually the structural connectivity profile of them, what we're going to get with tractography via this voxel is that these regions now are not going to be connected, and we're going to have connection from this region to both of them, right? Because of the confounds that I just described. And near the cortex, these ambiguities or biases will actually explode, because then you have a very, well, narrow gyrus, which is going to sample in a matter of a couple of voxels, and you're unable to distinguish these sort of very sharp projections, right, that project to the so-called walls, rather than just to the top of the gyrus. And to try and circumvent this, we have developed, which is also in FSL, we have developed an asymmetric model of fiber orientation distribution, which is actually capable of distinguishing fanning from bending and also determine the so-called polarity of the fiber, right? So should it fan out or should it fan in? And if this is the symmetric answer that, well, any modern algorithm will give you, given these three different scenarios, this is what the asymmetric fiber orientation distributions will actually give you. So the cancellation of the spurious cross that we have there, it will retain the crossing in the case where it's actually justified, and it will give you the ice cream answer, which just basically represents the fiber fanning polarity, right? So fibers should fan along this orientation, while actually they should pack if you were to see it from the cortex itself. And we tested that on some simulations and also in vivo. And basically here is the different answer in 3 different ROIs on a myelin histological stains, so an actually post-mortem stain in which you can see where the accents go to, and that is, those are the spurious or insufficient results that the symmetric analysis will give you, while if you use the asymmetric model, which is, again, just a simple modeling like we had the ball and stick before, you have the sharp bends here, but you also have the fiber fanning, correctly fanning there. So once again, different modeling approach, different answers, but they can help you when it comes to tracking results, when it comes to improving your tracking results. What you can do to validate your results is, of course, also to use multi-model approaches. So like in the Human Connectome project, you can use the functional data to interrogate structural functional relationship, because basically areas that are structurally connected to each other should communicate with each other. But actually what you get is that structural, because of a limitation of tractography and diffusion MRI analysis, you might get missing connection between two functionally connected areas. So if we look at this example at the bottom, we always do a seed approach, so seed connectivity approach at the bottom, using fMRI data, well, resting state fMRI data, task-based fMRI data, and diffusion tractography. And you see that seeding this from the same region will give you different connectivity profiles when it comes to the functional approaches and when it comes especially to comparing the structural results to the functional results. Well, actually, if you do invasive mapping of function and structure in, let's say, the macaque, you will get more coherent, well, as expected, results. And another thing, of course, from results that you can get out of tractography is the typical example of fiber crossing at the level of the cerebellum. So if you were to seed, if you're interested once again in the corticospinal tract, you know that fibers should decussate at the level of the bones. So seeding from one hemisphere should reach the contralateral cerebellar hemisphere. But actually, of course, because of the constraint that you impose with tractography, it will preferentially follow the most collinear path, ending in the ipsilateral cerebellar hemisphere, which is anatomically implausible. But even here, it's not that functional MRI can help you, because also functional MRI doesn't have a clue about laterality, right? So if it sees a correlated activation in both the hemispheres, it will give you that, right? So also fMRI is not capable of helping you in distinguishing this decussation behavior of white matter fibers. And that's all I had to say. Thanks very much for you to listening and to my collaborators. Cheers. Sure.
We were always talking about reducing this isotropic diffusion in white in gray matter. But in fact, the fibers are projecting into the gray matter.
Sure.
And they fund
Yeah.
different. So how can you
Yeah.
handle that?
So,
And
but
my second question is like, you have talked about the asymmetry approach.
Mhm.
What about the ball and rackets? Has this been the ball and rackets model?
Sure. So that is,
Been implemented in SSL somehow, or
it's
just too complex to?
it takes a very long time unless you have because of the number of parameters that you need to estimate. You definitely need a GPU to be able to estimate that.
Is it available?
I'm not sure whether it's in the release. I should double check that, but I know that it should be there, or at least, well, we're planning to move like those kind of modeling to allow you to develop your own models in the new toolbox that we developed. That is called CUDIMod, and that is basically a microstructural modeling toolbox that allows you to come up with your model and then just compile it, just estimate it directly on the GPU in a very quick fashion. Because usually these approaches take a very long time, right? So if you come up with your own parametric way of analyzing diffusion MRI data, you just have to effectively write the equation, the model of your equation, and estimate the parameters out of that. So I need to double check about the ball and racket model, but this is the non-parametric approach of doing sort of what the ball and racket model does. So these go back to the spherical harmonics representation of a diffusion signal, and using basically the neighborhood information, we're capable of obtaining asymmetric fiber orientation functions, right? This is how it roughly works. No, because again, this goes back to the idea of having an orthonormal basis defined on the sphere, right? So the spherical harmonics basis that we have. So it is a surface. It doesn't get you all the different parameters for the different fiber populations, but it kind of inherently does ARD, like in this example here. Yeah. So in gray matter, that's a good question. You would need, so there are more advanced models that are capable of analyzing data coming from gray matter. Just because in gray matter you have, like I said before, water more freely diffuses, but it's true, you do have a certain degree of anisotropy given by the fibers that enter the cortex. So yeah, you need more advanced modeling for that, but it's certainly possible. It's also a matter of resolution, right? So the human cortex ranges between what, 2 and 4 millimeter at max, yeah? So with current resolution, it's very tricky to get this nice insertion into the cortex. Yeah.
What about the probabilistic max of derived from practice? So there is a way of threshold that can balance between two axon trajectory versus invalid or false positive results.
So you mean about, so not the bedpost not the anisotropic volume fractions, that you can, let's say, threshold at 5%, but actually the path probability maps.
The path probability.
So yeah, sure. You can also, so given that these are weighted representation of your paths, you can threshold them, and typical values range from 0.01 to, or, well, close to that, let's say, for a minimum. And that will already clean up your results quite a lot. But it's based on your pre-anatomical knowledge, basically, right? So it isn't a very much grounded. So the more grounded way is to apply approaches like using the different maps, the exclusion map, waypoint maps, and so on and so forth. And then, of course, visually checking the results to be able to remove false positive or false positive connection, right? But then becomes a question: what is a false positive connection? Right? Are you really sure that that weight will correspond to that? So.
I could imagine that it's easy to do on the cortical spinal tract,
Mm-hmm.
but then to do, for example, on the
Yeah, not even that,
should
probably.
be
Yeah.
problematic.
Yeah, but that's why. Yeah, but that's why you should go to the validation approaches, right?
Yes.
And try to, yeah. The golden idea would be, to define a threshold that works for all the connections. Yes.
The track density thing that you showed with the super cool video model, is that implementing Amazon?
Yes, we do have that. Yeah.
And that, I've never heard of it before, so that can be applied to sort of regular diffusion data, sort of 2 millimeter long.
Sure, absolutely. So I think, I'm not sure, but I think that was applied to 2 millimeter isotropic boxes. I mean, you can imagine, of course, that yes, if your base acquisition is amazing, like the HCP and like DHCP, this kind of data, you're going to get even better description than what you would get by regrading 2 millimeter data.
And can you combine that with the tractography probably?
Sure. So to get to track density images, you need to have run probabilistic
It's
tractography.
run off of,
Yeah, absolutely. Yeah, it's literally like a regrading of your path probability maps.
and then you can do metrics on.
Yeah, but yeah, there are some people that do that. But yeah. Yes. So you can use the waypoint masks, for example. Yeah, absolutely. But even if you do that, you're not effectively telling when you track, follow the path, which is now not the most collinear one, but it's actually the one that decussates, right? You're just saying retain those streamlines that reach that hemisphere, right? So you're removing the super strong connections, right, which get to the cerebral hemisphere that you're not interested in, but you just effectively boost the very low connections that you would otherwise get.
I'm sorry to interrupt.
No, I'm done.
Can I have 5 to 10 minutes of lunch break?
Sure.